Imagine driving for over 30 miles across the open ocean without ever boarding a ferry. Now imagine that halfway through the journey, the bridge simply disappears beneath the sea, turning into an underwater tunnel before rising back above the waves as if nothing happened. It sounds impossible, but every single day, thousands of people make this journey across one of the most dangerous stretches of water in Asia. This wasn't just another bridge. It had to survive category-level typhoons, a magnitude 8 earthquake, and even a direct collision with a fully loaded cargo ship. To build it, engineers poured millions of tons of concrete, used enough steel to build 60 Eiffel Towers, and spent nearly $20 billion creating something no country had ever attempted at this scale. The result was a 34-mile sea crossing connecting Hong Kong, Zhuhai, and Macau for the very first time in history. But building it meant solving engineering problems many experts believed couldn't be solved. This is the story of how China built the Hong Kong, Zhuhai, Macau Bridge, the longest sea crossing on Earth. To understand why this bridge needed to exist, you have to understand the geography it was fighting against. Hong Kong, Macau, and the mainland Chinese city of Zhuhai all sit around the mouth of the Pearl River, one of the busiest and most economically important waterways in the world. On a map, these three cities look close enough to touch. In reality, for most of modern history, they were separated by open water, meaning anyone traveling between them had almost no choice but to take a ferry, a journey that could easily eat up an hour or more each way, subject to weather delays and unpredictable schedules. By the early 2000s, this wasn't just an inconvenience. It was becoming an economic bottleneck. The region surrounding these three cities, known as the Pearl River Delta, had exploded into one of the most productive manufacturing and trade corridors on the planet, home to tens of millions of people and a huge share of China's export economy. Goods, workers, and business travelers were moving between these cities constantly, and every single trip was bottlenecked by water. Chinese planners, working alongside engineers from Hong Kong and Macau, began seriously studying a fixed land link as early as the 1980s, but the idea didn't gain real momentum until China's economic rise accelerated in the 2000s. The bridge wasn't just about convenience. It was the physical centerpiece of a much larger economic strategy. Beijing began actively planning what it would eventually call the Greater Bay Area, an ambitious plan to integrate Hong Kong, Macau, and 9 mainland cities into a single interconnected economic superregion, similar in ambition to how the San Francisco Bay Area functions as one connected economic zone rather than a collection of separate cities. The problem was that connecting these three specific cities wasn't like building a normal bridge. Hong Kong and Macau are separate legal and political jurisdictions from mainland China, each with their own governments, currencies, and legal systems, a legacy of Hong Kong's history as a former British territory and Macau's history as a former Portuguese colony. Any crossing connecting them wouldn't just be an engineering project. It would be a three-way political and financial negotiation between two special administrative regions and the mainland government, each with different priorities and different ideas about funding and control. Construction officially began on December 15, 2009, following years of negotiation, environmental review, and engineering feasibility studies. What these engineers were about to attempt hadn't really been done before, not at this scale, across 34 miles of typhoon-exposed open ocean. The single biggest design challenge facing engineers wasn't how to build a bridge across open water. It was what to do about the Pearl River Delta's other defining feature. It is one of the busiest container shipping routes in the world, with massive cargo vessels moving in and out of the port of Hong Kong around the clock. A conventional bridge tall enough to let these ships pass underneath would have created serious structural risks in a region regularly hammered by typhoons. Engineers needed massive ships to pass through the busiest section of the crossing completely unobstructed, with nothing overhead at all. Their solution was almost audacious. Instead of one continuous bridge, they built a hybrid structure. Long cable-stayed bridge sections carry the crossing across most of the open water. But directly over the primary shipping channel, the road dives underground, running through a 6.7-kilometer undersea tunnel, letting the largest cargo ships on Earth pass directly overhead with zero interference. That created a new problem. A road can't simply drop from bridge height straight into an underwater tunnel. Engineers built two entirely artificial islands from scratch in open ocean, each roughly 10 hectares, constructed by driving massive steel cylinders into the seabed and filling the enclosed area with sand and rock, creating solid landing zones where the bridge sections connect into the tunnel entrances. The undersea tunnel itself remains, to this day, the longest immersed tunnel built for road traffic anywhere in the world. Instead of boring through solid rock the way a mountain tunnel would, engineers used a technique called the immersed tube method. Massive prefabricated concrete tunnel sections were built on land, each one weighing tens of thousands of tons, then floated out to the exact tunnel location and carefully sunk into a trench dredged into the seabed. Each segment had to connect to the next along the ocean floor with extraordinary underwater precision, essentially assembling a tunnel piece by piece, 30 meters or more below the surface of the sea. Even a small manufacturing error in a single segment could have made it impossible to seal one section against the next once submerged. Engineers positioned each piece using GPS-guided precision, working around shipping schedules for one of the busiest ports on the planet, and around a seasonal typhoon calendar that could halt operations for days or weeks at a time. The overall crossing combined 3 separate cable-stayed bridges, each with its own distinct tower design, connected by viaduct sections feeding into the artificial islands, feeding into the tunnel, feeding back out onto more bridge. One seamless road built from 4 or 5 entirely different categories of construction. Every single piece of this crossing, 3 separate bridges, 2 artificial islands, and 1 undersea tunnel, had to line up perfectly across 34 miles of open water, with zero room to adjust once construction was underway. Unlike a normal road project, engineers couldn't simply pour concrete and correct small errors later. A tunnel segment sunk even slightly out of alignment on the seabed could make it impossible to seal against the next section, potentially compromising the entire crossing. To solve this, engineering teams relied on advanced satellite positioning systems combined with underwater sonar mapping, allowing survey crews to track the exact location of each tunnel segment, each island foundation, and each bridge pier to within centimeters, even while working across a stretch of ocean longer than the distance between many major American cities and their airports. This level of precision had to hold steady across nearly a decade of construction, multiple contractor teams working independently on different sections, and constant exposure to shifting tides, currents, and seasonal storms. Engineers were essentially building one continuous, perfectly aligned structure out of dozens of separate megaprojects, each one being constructed by different crews in different locations, all required to meet in exactly the right place, at exactly the right depth, years apart from each other. Almost every major decision engineers made was shaped by one brutal fact. The Pearl River Delta sits directly in the path of some of the most powerful tropical storms on the planet. Engineers designed the bridge sections to withstand sustained wind speeds of up to 160 kilometers per hour, roughly 100 miles an hour, blowing directly against a structure stretched across open water with no natural windbreak in any direction. That required rethinking the aerodynamics of the bridge towers and deck sections almost from scratch, using wind tunnel testing to model exactly how storm force winds would move across the structure, and designing the roadway deck to let wind pass through rather than catching it like a sail. Earthquakes posed a separate threat. While the region isn't as seismically active as some parts of the world, engineers designed the bridge and tunnel system to withstand an earthquake up to magnitude 8, a level of resilience typically reserved for far more earthquake-prone regions, built in as a safety margin against the kind of rare but catastrophic event that could take an entire crossing offline permanently. With one of the busiest cargo shipping lanes on Earth running directly beneath and alongside the structure, engineers had to seriously plan for the possibility of a large vessel colliding with a bridge pier or tunnel section. The bridge's piers were reinforced with dedicated anti-collision barriers, engineered specifically to absorb and deflect the impact force of a large ship strike without triggering structural failure. A lesson drawn partly from historical bridge collapses elsewhere in the world caused by exactly this kind of vessel collision. The sheer quantity of steel involved is difficult to picture. In total, construction used roughly 420,000 tons of steel, more than 4 times the total steel content of San Francisco's Golden Gate Bridge, reinforcing everything from the bridge towers to the underwater tunnel segments to the artificial islands themselves. Every component was designed with a working lifespan of 120 years, meaning engineers weren't just solving today's traffic problem. They were building infrastructure meant to still be functioning through most of the 22nd century, decades after everyone who built it will be gone. Construction stretched across nearly 9 years, from the 2009 groundbreaking through completion in 2018, involving tens of thousands of engineers, laborers, and specialized marine construction crews working simultaneously across dozens of sites: bridge tower foundations, artificial island construction, tunnel segment fabrication yards, and deep-sea placement operations, all running in parallel across 34 miles of open ocean. This was one of the most logistically complicated construction projects ever attempted at sea. Massive concrete tunnel segments had to be built onshore to extremely tight tolerances, floated out, positioned with GPS-guided precision, and sunk into an underwater trench with almost no room for error, all while working around shipping schedules and a seasonal typhoon calendar. The project carried a real human cost. Reports confirmed 9 workers died during construction, with an additional 275 reported injuries across the 9-year period. Figures that drew public criticism in Hong Kong specifically, where lawmakers and worker advocates raised concerns about safety oversight and pushed back against what they characterized as understated official casualty figures. Behind the record-breaking statistics, this was ultimately built by thousands of people working in dangerous, demanding conditions for the better part of a decade. The project also became a serious flashpoint for environmental concerns. Conservation groups, including WWF Hong Kong, raised alarm over the bridge's impact on the region's population of endangered Chinese white dolphins, a species already under severe pressure from shipping traffic and habitat loss in the Pearl River Delta. Studies conducted during and after construction reported significant declines in local dolphin sightings in waters near the bridge, with populations in the hardest-hit areas dropping by as much as 60% during the peak construction years. The controversy continues to shadow the project's legacy even years after its completion, a reminder that engineering triumphs rarely come without ecological trade-offs, especially when the construction site is also a living habitat for an endangered species. Critics have pointed to the dolphin decline as one of the clearest examples of how large-scale infrastructure, however impressive, can carry consequences that extend well beyond the construction budget and the concrete itself. The final cost of the bridge came in at approximately 127 billion Chinese yuan, or roughly $20 billion US, once every phase of construction was accounted for, making it one of the most expensive bridge projects ever built anywhere in the world. Financing a project of this scale required an unusually complex arrangement between 3 separate governments. Mainland China, Hong Kong, and Macau each contributed funding and jurisdiction over their respective sections, requiring years of negotiation over cost-sharing and construction standards, since the bridge would ultimately cross through 3 separate legal systems under one physical structure. That complexity didn't disappear once construction began. The project faced repeated delays and budget overruns, including a widely reported legal inquiry into environmental and safety standards on the Hong Kong side that pushed the original 2016 opening date back by roughly 2 years. Critics also raised pointed questions about toll pricing once the bridge opened, arguing that high crossing fees discouraged private vehicle use, even as the bridge dramatically cut travel time for buses and freight. After nearly 9 years of construction, the bridge officially opened to traffic on October 24, 2018, in a ceremony that drew international attention, widely covered by outlets from the BBC to CNN as the unveiling of the world's longest sea-crossing bridge. The impact on daily travel was immediate. A journey between Hong Kong and Zhuhai that once required a ferry ride of an hour or more, or a road trip of up to 3 hours, could now be completed in as little as 30 to 45 minutes. Access to the bridge came with unique restrictions reflecting the complicated political geography it was built to bridge. Private vehicles from Hong Kong require special cross-border permits, while most travelers instead use dedicated shuttle bus services, still clearing immigration and customs between jurisdictions even while physically crossing on one continuous structure. A reminder that even the most impressive physical engineering couldn't fully erase the political boundaries it was built across. The Hong Kong-Zhuhai-Macau Bridge is often reduced to a single statistic, the longest sea crossing on Earth. But the number that actually matters is harder to put on a plaque. It's the sheer number of separate, nearly impossible engineering problems that had to be solved simultaneously. The wind loads, the seismic risk, the shipping lanes, the underwater tunnel assembly, the artificial islands built from nothing, and 3 separate governments that all had to agree on how to build it. Long after the ceremony ended, what remains is a structure that quietly performs one of the most difficult balancing acts in modern engineering every day. Carrying tens of thousands of vehicles across open, typhoon-exposed ocean, diving beneath one of the busiest shipping lanes on the planet, built to outlast every person who worked on it. The bridge's legacy remains genuinely complicated, a symbol of extraordinary engineering ambition, and at the same time, a case study in the real human and environmental costs those ambitions can carry. But taken together, it stands as proof that even 34 miles of hostile ocean can be engineered into a single, unbroken road, if a nation is willing to commit the money, the decade, and the technical audacity it takes to build it.